Okay, welcome to EGR445. In today's class, we will solve some spur gear problems, and then we will talk about how can we extend what we learned in last class to design helical gears. Now, please understand, design procedure for helical gears is similar to spur gears. So, for the purposes of design, we will convert a helical gear into an equivalent spur gear and then perform the analysis. But recognize the shaft design for spur gear and helical gear will be slightly different. So what we are going to do is we'll start with one problem. And there are few variations that are possible. So I will try to address all possible variations. So for an example, design a single reduction spur gear. And the gear ratio is equal to 10:1, which means one revolution of the gear will cause 10 revolutions of the pinion. Now in this problem, center distance is given. One thing I just want to point out that even though the center distance is specified, it is very difficult to maintain the exact center distance when you have a gear pair. So typically you compensate or you allow for some deflection by adjusting or adding tolerances when you design the bearings that actually used to support the shaft. So now the pinion transmits power is equal to 500 kilowatt. And I just want to tell you that this power 500 kilowatt is quite significant. So I wouldn't expect this power to be transmitted at very high speed. I would expect this power to be transmitted at low to moderate speeds. So RPM is equal to 1800. So the pinion is rotating at 1800 RPM. What that means, the gear is rotating at 180 RPM. Now it is an involute profile. And pressure angle is equal to 22.5. And I want you to take a note of this. This is a non-standard pressure angle. This typically the pressure angles are 14.5 or 20 degrees. This pressure angle is 22.5. So this is probably a very special application. And permissible normal pressure between teeth is equal to 175 newtons. Now, if you think about it per millimeter, now this is one way of specifying the contact load, which means we are just saying that the normal pressure between two meshing teeth cannot exceed more than 175 Newton per millimeter. Now we have to find out, so determine first the module, second number of teeth, third width of the pinion, and D, the bearing load. So let's try to understand how is this gear pair schematically. So you have this large gear, and then we have this small pinion. So clearly the large gear is 10 times the pinion. So I'm going to call this radius of gear, and I'm going to call this radius of pinion. Now the gear ratio is 10. What that means is speed of the pinion divided by the speed of the gear. NP is the speed of the pinion speed of the gear is equal to 10. This also means radius of gear divided by radius of pinion is equal to 10. Now, it can be observed that the center distance is 660. So you can notice what this means is RG, radius of gear, plus radius of pinion is equal to 660 millimeter. Now, this is one important piece of information that we have to use. Now, first and foremost, we have to find out the module. Now, whenever we start designing a gear and pinion pair, and I can show this schematically, something like this. So this is the gear, this is the pinion, and you have this shaft here, and you have the pinion shaft that is over here. And these shafts are supported by the bearings. So this is how a gear transmission is shown schematically. Now, we know RG plus RP is equal to 660. But we need to make sure that minimum number of teeth on pinion are maintained so that there is no interference. And at this point, I would encourage you to go back to the table that we discussed in last class, wherein we suggested minimum number of teeth to avoid interference. So if you follow through the notes that we discussed in last class, you would observe the minimum number of teeth on pinion to avoid interference is 14. The alternate way is you can actually use the equation that has the modulus of rigidity and the pressure angle equation, but I would usually stick to the data book. So minimum number of teeth on the pinion to avoid the interference is 14. Now in this particular case, the gear ratio is given. Okay, so gear ratio can also be written as number of teeth on gear divided by number of teeth on pinion. So if I know TP is equal to 14, that are the number of teeth on the pinion are 14, that means number of teeth on gear is equal to 140. Now this, at this point, there is no design. We are not checking or we are not finding out parameters using the design equations that we studied in the last class. So these dimensions, are determined using geometry constraints. So now what I can do is I can rewrite equation 1. As we know, pitch circle diameter is equal to module multiplied by number of teeth. So PCD of gear is equal to module times number of teeth on gear. PCD of pinion is equal to module times number of teeth on pinion. Please note, module is the most important design parameter for gear and pinion. It has to be the same. Number of teeth could be different, but the module and other gear parameters like addendum, dedendum, they have to be same on pinion and gear. So now I can rewrite the equation that we found out. Radius of gear plus radius of pinion is equal to 660. Radius is equal to diameter divided by 2. So module multiplied by number of teeth divided by 2 plus module multiplied by number of teeth for pinion divided by 2 is equal to 660. Now this gives me module, so 14 plus 140 divided by 2 is equal to 660. That means I now have the answer for my module, and that module is about 8 millimeters. About 8 millimeters. Now the key question at this point is, if your module is greater than 8.5, 8.6, or if your module is in some decimal point, say 8.2, 8.3, it's always the good idea to round it up on the higher side. So round it to the higher side. Because this is the minimum size or minimum dimension that we need so that the design or the gear is safe. Now, in the second step, we have to find out number of teeth. And please note, we already determined number of teeth on pinion and number of teeth on gear. So number of teeth on pinion, which is T pinion, is equal to 14. T gear is equal to 140. Now next thing is, we have to find out the width of the pinion. width, which is nothing but B. Please understand, this B dimension will be same for gear and pinion. So this dimension is going to be the same for gear and pinion. Now at this point, I want to pose an important question. Say you have the gear something like this, you have the pinion something like this. And the teeth are sort of coming in contact at this location. In this particular problem, what they have done is, instead of giving us the values for the contact stresses, they have just told us that the force, permissible normal pressure. So this is permissible normal pressure is equal to 175 Newton per millimeter. Now, the question here is why this permissible normal pressure is given. And the most obvious reason for that is because this is a non-standard gear. So if you look at the pressure angle, this pressure angle is 22.5. So this is sort of a non-standard pressure angle. That's why they have given us the permissible normal pressure. So what does this permissible normal pressure mean? It means that the force. So let me talk about, so you have force here. The force that is acting on the gear surface, so that needs to be sort of spread across the width. So let me explain what I mean by that in just a second. So what I want to show you here is just a single tooth. This is the tooth. And this dimension is B. If you look at this force is actually spread across this line because there is going to be a line contact, which means this pressure, this force divided by B is going to be the pressure. And this pressure is nothing but the permissible normal pressure. To find the permissible normal pressure, first we have to find out the value of the force. And this force value, please understand, you can see that this is the radius of the gear, this is the radius of the pinion, and the values of torque are going to be different for the pinion and gear. So this is an important observation. So torque of the gear divided by torque of the pinion, torque of the gear divided by the torque of the pinion is speed of the pinion divided by the speed of the gear is equal to the gear ratio, which is 10. And you can actually go ahead and rewrite the gear ratio in terms of the number of teeth, and you will also obtain the same relationship. So in this particular problem, I want to highlight here that the power transmitted by pinion is given. This is the same amount of power that is transmitted by the gear. But what I'm going to do is I'm going to say P is equal to 2 pi n t divided by 60, where P is the power, T is the torque. Power is given as 500 kilowatts. Is equal to 2 times pi multiplied by the speed of the pinion. And as we know, the speed of the pinion is 10 times the speed of the gear, and the speed of the pinion is given as 1800. So I would write this down, 1800 multiplied by T divided by 60. From this, I'm gonna get torque on the pinion, and this will be in Newton meter. Once I find out the torque on the pinion, I need to use this information to find out the force on the pinion. So force on the pinion, F pinion, is equal to torque on the pinion divided by the radius of the pinion. So torque on the pinion, my answer is 2652 Newton meter divided by the radius of pinion we already know, which is 0.12 divided by 2. And that gives me 44.2 kilonewton as the force. Now the pressure is given. The value of the pressure is given to us. But I want to emphasize here that this pressure, and this is important, this pressure is nothing but the normal pressure. So this is normal pressure. So which means this is normal force divided by B. And this FP is nothing but the tangential force that is causing the torque to be transmitted. So to find out the normal force, please refer to your equation that we derived in last class. That is going to be Fp divided by cosine of pressure angle, which is 22.5, divided by value of B is equal to 175. And from here, FP, FB, no, FP, sorry, FP comes from here, FP comes from here. And then when you find out the value of B, B is equal to 275 millimeter. So this is a very wide gear. Now the last part is the bearing load. So load on the bearing. And load on the bearing is nothing but the radial force. And we talked about this in the last class. Radial force is Fp multiplied by tan of pressure angle, or normal force multiplied by sine of pressure angle. You can use any equation and you will find out this is 44.2 tan of 22.5. 0.5, and that gives me 18.3 kilonewton. So this is the gear design based on the geometric constraint. Now, I just want to point out in this problem, we did not use the strength or beam strength equation or Levy's equation. We did not check for gear where we did not check gear for where, because this was a non-standard design and the magnitude of bearing the normal pressure was given to us. So what I'm going to do is now I'm going to take a design problem wherein what we will do is we will actually use the technique or the recipe that I gave in last class to solve the problem. Before we proceed, any questions? Okay, next problem. So spur gear design. And the power to be transmitted, P, is equal to 20 kilowatt. So we have to transmit 20 kilowatts. The speed of the pinion, NP, stands for pinion speed. And this pinion speed is 300 RPM. So pinion is rotating at 300 RPM. The velocity ratio, which is another name for the gear ratio, is equal to 1:3. What that means is 1 revolution of gear causes 3 revolutions of pinion. 1 revolution of gear causes 3 revolutions of pinion. Allowable static stress. For gear and pinion, they are given as, so for pinion, allowable static stress for the pinion material is 120 megapascals, and for gear it is 100 megapascals. So please note that we don't have the same material for the pinion and gear. The material for the pinion and material for the gear, they are different. Now next part is the number of teeth on pinion, TP, number of teeth on pinion, they are 15. And the face width, so B, is equal to 14 times module. So in this problem, the number of teeth on pinion are given. The face width to module relationship is given. So this is face width and this is module. So face width to module relationship is given. So we have to find out first module, then face width, then C, it's PCD of gear and pinion. PCD of gear and pinion. Now, good news is they have given us value of Y, which is the Lewis form factor, or also called as the tooth form factor, which is 0.154 minus 0.912 divided by number of teeth. And the velocity factor, CV, is given as 3 divided by 3 plus V. So typically, these values we find from design data book, but in this problem, these important relationships that we need for gear design are already given. So the idea here is we are progressively going to make problems complex. So in here, the major parameters, equations, CV, etc., they are given. The strength values are given. So it's sort of following the recipe and finding the answer. The next problem that we'll take will be sort of an open-ended problem where we will actually refer to the design data book and then select the appropriate values. But nevertheless, the general procedure is going to remain the same. So first and foremost, what I'm going to do is we are going to find out module. So step 1, determination of module. So in this case, so what we will do is we'll find out the pitch line velocity. Once again, pitch line velocity is the velocity of the pitch point. This is P. So pitch line velocity is the velocity of the pitch point, and whether you consider pinion or you consider gear, by the law of gearing, this velocity has to be the same, whether you consider it the point P on the pinion or point P on the gear. However, an important observation here is pinion speed is given to us. The speed of the pinion is 300 RPM. So what I'm going to do is I'm going to find out the pitch line velocity considering the pinion RPM. So I'm going to find out the pitch line velocity considering the pinion. So VP on pinion is equal to pi times diameter of pinion multiplied by speed of pinion divided by 60. Now pitch line velocity, I'm going to find out in meters per second. That means the diameter of the pinion has to be in meters. And since we are dividing that equation by 60, the speed of the pinion has to be in RPM. But here is the thing. In this problem, unfortunately, the diameter of pinion is not known. So diameter of pinion is not known. However, we know the relationship between the module and number of teeth. So the diameter or pitch circle diameter is equal to module times number of teeth. So what I'm going to do is, I know from this problem, the number of teeth on pinion are 15. So I will substitute 15 times m is equal to diameter to the pinion. And I will find out the velocity of pinion. Pitch line velocity, considering point P on pinion, is pi times 15 times m multiplied by 300 rpm divided by 60. Now what this means is I'm going to get the velocity of pinion in terms of module. So this is very important. I'm going to find out the velocity of pinion, Vp, considering pinion, in terms of module. That is 0.23 m meters per second. So I have V, that is the pitch line velocity, at 0.23 multiplied by module. And depending upon what the value of module is, this answer will be different. Now, what we need to do is, at this point, they have not given us the service factor. Remember CS, service factor. This service factor, it's kind of a factor that talks about the duty cycle, whether that gear transmission is continuously working, intermittently working, or subjected to heavy loads or steady loads, either the gear is starting, stopping, so on and so forth. Since service factor is not given, I'm going to assume CS, which is service factor, is equal to 1. So the service factor will be assumed as 1. With this service factor, I should be able to find out the tangential load, which is power divided by the pitch line velocity multiplied by the service factor. So power is the power transmitted, V is the pitch line velocity, and CS is the service factor. Now at this point, I just want to make a comment. Power is the same for pinion and gear, because the same power is transmitted from pinion to gear. So power is same. Pitch line velocity is same for pinion and gear. So it doesn't matter what value you choose, you are gonna get the same value of WT. So in this case, I'm gonna substitute the values that we already found out. 20, I will convert this power into watts. 20 10 to the power 3 divided by 0.23 m multiplied by 1. That gives me the value of WT. Now, with this WT, what I need to do now is use this WT and use the gear tooth loading equation to find out the actual module. So please observe here, the next step is we have to know what is the velocity factor. So CV is the velocity factor. And this velocity factor is to take into account the fluctuating load. So this velocity factor is to account for fluctuating load, and that is given as 3 divided by 3 plus V. Now, however, please note, we don't know the exact value of V. The pitch line velocity V is given in terms of module, so which is 3 plus 0.23 m. 0.23 m. So this service factor, the velocity factor is actually a function of module. Now, what we know is the Lewis factor or the tooth form factor, which is y, is given as 0.154, and it is given in the problem minus 0.912 divided by number of teeth. So what I'm going to do is, first and foremost, I'm going to find out this value of y for gear and pinion. Now, a side note. At this point, we have to find module. Now, to find module, we can use the dimensions of the gear, or we can use the dimensions of the pinion, or we can use the gear material or the pinion material. But first, we need to find out of this gear and pinion, which one is weaker. So we need to find out whether the gear is weaker or whether the pinion is weaker. And in this problem, why is this specific step required? Because the gear material is different. So since as the materials are different. Now, if the materials are the same, which means the gear and the pinion, both of them are made up with same material, in that case, pinion is always weaker. But since the gear and the pinion, they are made up with two different material, first and foremost, we have to find out which one is weaker. So what I'm going to do is, before proceeding further, I need to answer this question, whether gear is weaker or pinion is weaker. So what I'm going to do is, I'm going to do the beam strength calculation for gear. So first, let's do it for pinion. So pinion. So the way we do it is, y for pinion is equal to 0.154 minus 0.912 divided by number of teeth on the pinion. So in this case, the number of teeth on pinion are 15. So YP is 0.09. Now the strength of the pinion. So strength of the pinion, sigma pinion, is given in the problem, which is 120 megapascals. So 120 megapascals is equal to 120 Newton per millimeter square. So what I'm going to do is, in the next step, I'm going to find out the product of sigma P times YP. So this is 120 multiplied by 0.09. Similarly, I will perform the same calculations for gear. So I will find out Y of gear is equal to 0.154 minus 0.912 divided by. But please note, now here we need the number of teeth on the gear, and that is 15 times 3. These are the number of teeth on gear. That gives you value of YG, and observe this value of YG is 0.13. This is greater than YP. But sigma G, which is the strength of the gear material, is given as 100 megapascals. So this is 100 megapascals is equal to 100 Newton per millimeter square. Now what this means is sigma g times yg is equal to 100 multiplied by 0.13. And you will notice that this answer is about 11 and this answer is about 13. So what this means is pinion is weaker. So pinion is weaker. And when the pinion is weaker, that means we have to design for pinion. Everyone understood this step. This is an important step, and this is something that we will have to do in helical gear design, in bevel gear design, that we have to find out whether the pinion is weaker or the gear is weaker. So with this, we will start. As pinion is weaker, module will be designed based on pinion. So the next step is quite straightforward. Remember the beam strength equation. WT is equal to sigma W multiplied by B multiplied by pi times module multiplied by the Lewis form factor. So sigma W is nothing but the strength, and this sigma W, I need to write this down. I'll do this for the first exercise. Sigma O multiplied by the velocity factor. B pi m yp. Now sigma O for pinion, please note sigma O for pinion is 120 megapascal. So this is 120 multiplied by the velocity factor. We already found out 3 divided by 3 plus 0.23. So this is the velocity factor. Multiplied by B. Now recognize B is already given as the ratio. So the value of B, the face width, is 14 times module. So I will substitute B is equal to 14 times module pi module multiplied by y of P, which is 0.09. And WT is a tangential load. And please note, we have found out the tangential load from this equation. Which is 20 to 10 to the power 3 divided by 0.23 m. Now this equation may look complex, but in reality is not, because the only unknown here is module. We don't know what the module is. Everything else is known. So this is a cubic equation. Sorry, it is actually, cubic equation. But one thing I want you to understand, that you have m in the denominator as well. So this equation cannot be directly solved. So this can be solved either using trial and error, or if you have a scientific calculator like TI-84, you can program this equation and So TI-84 can solve this equation using some solve command. So you can come up with this equation and TI will give you the answer. And I would like you to practice this a bit. So just try to program this equation or try to solve this equation using trial and error and then try to get the answer. But if you are trying to find out the answer using trial and error, how would you do it? So I'm going to explain trial and error approach. Trial and error approach. So we don't want you to perform hundreds and hundreds of trials. So what we need to do is we have to start with some baseline n, and then iterate back and forth and see what answer we get. Now, here is a quick trick. So assume 3 divided by 3 plus 0.23 m is equal to 1. So assume 3 divided by 3 plus 0.23 m is equal to 1. And this is an assumption. When that is, if you assume this, your equation happens to be 10 to the power 3 divided by 0.23 is equal to 120 multiplied by 14 multiplied by pi multiplied by 0.09 multiplied by m cube. So if you assume the velocity factor is equal to about is equal to 1, then what you can do is you can see that this equation reduces to just a cubic equation, and that gets you what you value of m is equal to some, it will give you some starting value of m. Now the next step is you increment this value a little bit. So for an example, let's say from here we got the value of m is equal to, I'm just guessing, 6 millimeter. Now what I'm going to do is I'm going to go ahead and do 2 iterations. I'm going to say I will do the iteration for say 4 millimeter, and I will do the iteration for 8 millimeters. And when I'm going to do these iterations, I'm going to use the equation that is over here. And when I do this iteration, I will see whether the left-hand side is equal to right-hand side or not. And then depending upon what answers I get, I will tweak it near the values. So usually when you do the trial and error with this approach, you should be able to get close answer in 3 tries. So first you will assume m is this velocity factor is equal to 1, then find out the value of module and iterate on the higher side and on the lower side, and then somehow converge on the value of m. If that is a little bit complicated method, then you can actually just try to program this using TI or some online calculator, and that should be able to give you the answer. One good online calculator to solve these types of approximate equations is something called as Desmos. So online calculator is called as Desmos. And this is a good calculator. You can actually program your equations, and then it will actually solve this equation approximately. and then give you the answer. It can actually generate the plot and show you the convergence as well. All right, the next step is determination of phase width. So phase width determination is very simple. So 2 is phase width. This phase width is we already know, which is 14 times module. So 14 times module. And for this problem, the answer is 8 millimeters with trial and error. Trial and error answer is 8 millimeters. So phase width is 14 times 8. Which is 112 millimeter. And the last part is the pitch circle diameter. And the pitch circle diameter is module times the number of teeth. So the pinion has how many number of teeth? 15. Yeah, so we found out the number of teeth on pinion is equal to 15 here. So 8 times 15, 120 millimeter. And for gear, 360 millimeter. So this is how we will solve the problem. Any questions here? Now let's take a complete problem wherein what we are going to do is we are going to start from the basics, and then we will try to design the gear, and then from there we will try to design the shaft. So next problem. So design gear where the power transmitted is 15 kilowatt. So the power that is transmitted is 15 kilowatt. The low speed shaft, or basically the gear speed, which is ng, is 1500. So gear speed is 1500. The speed reduction or gear ratio is equal to 1:3, which means 1 revolution of gear is causing 3 revolutions of pinion. Now, the teeth, the pressure angle is equal to 14.5. So the pressure angle is 14.5. And number of teeth on pinion is equal to 25. So in this case, the number of teeth on pinion are given. Gear and pinion are made with same material and the value of safe stress, which is sigma O, is 200 megapascals, which is 200 Newton per millimeter square. And the stress for the shaft, tau shaft, is equal to 40 Newton per millimeter square. 40 Newton per millimeter square. And then we have to, and they are saying that assume starting torque is equal to 25% higher than running torque. So in this problem, this is a little bit open-ended problem in the sense that the power requirement or the power transmission capability of the gear is given, the speed of the gear is given, the gear ratio is given, the pressure angle is 14.5, number of teeth on pinion, they are given as 25. And the good news is the gear and pinion are made up with same material, which means the pinion is going to be weaker. However, there is something interesting that you want to take a note of is in this particular case, the starting torque is 25% higher than the running torque. And it's usually the case because when the machinery is at rest, there is stiction and there is inertia that needs to be overcome when the gear or the transmission is starting. So the initial torque, the starting torque is typically higher. So in this case, they are talking about starting torque to be 25% higher than the running torque. So what we are going to do is we are going to use this information to design the gear. And in this case, they are saying that along with gear, design the shaft as well. So that's why they have given us the value of the safe stress for the shaft. So this problem is solved in 2 steps. What we have to do is we have to find the gear parameters, design the gear, then use the information from the gear and design the shaft. But one thing that is important to note that they did not specify how the gear is mounted. What that means is it is not stated whether the gears are attached like this or the gears are attached like this. So this information is not given. And please understand the configuration of the gear plays an important role in shaft design. So at this point, what we will do is we will try to make some assumptions. So about the configuration. So we are going to assume configuration to design shaft. Sometimes it is explicitly mentioned that the gear is cantilevered or the gears are simply supported. So if that is specifically stated, then you have to stick to that particular configuration. And there are reasons for having the simply supported gears or cantilevered gears. Sometimes you need to accommodate a particular gear configuration in certain size. The housing shape needs to be particular so that it fits into the engine or the transmission. So there could be many reasons apart from strength that dictate the particular powertrain or the gear train configuration. So the first thing to note is the good news here is the number of teeth on pinion are given. This is an important piece of information, that number of teeth on pinion are given. The case is possible when the problem is just more open-ended, which means number of teeth on pinion not specified. And that is absolutely fine. So in that case, you will stick to what we did in the first problem, and you will assume the minimum number of teeth on pinion to be 14 to avoid interference. If number of teeth on pinion are not given, assume T pinion is equal to 14. The second observation here, gear and pinion made with same material that means pinion is weaker. And when the pinion is weaker, we have to design for the pinion. The last observation here is the speed of the gear is given, that information that we will use, and the service factor CS the service factor is equal to 1, and this is what we are assuming. So we are going to start. First and foremost, the starting torque is 25% higher than the running torque, which means starting power P starting is equal to 1.25 times P running. What that means is 1.25 multiplied by 15 kilowatts is the power that is needed to start the system. The next thing is we have to start with the gear ratio. We know number of teeth on gear is equal to 3 times number of teeth on pinion, because the gear ratio is 3. At this point, what we will do is we want to find out the value of the velocity factor. So is there any other information that is given to us? The other information is sigma O is given as 200 megapascals. So let me write this equation first, just very quickly. Pitch line velocity is equal to pi times d times n divided by 60. Now n is given for gear. So what I'm going to do is I'm going to find out pi times d gear times n gear divided by 60. So which is given as pi d gear is module multiplied by number of teeth on gear multiplied by n gear is 1500 divided by 60. So in this, I have this equation pi module number of teeth on pinion are given as 25. So 3 multiplied by 25 is equal to 75. So this is 75 times 1500 divided by 60. Now with this VP, I should be able to find out the velocity factor. Now here is something that we need to think about, the velocity factor. And at this point, I want you to go back to the table for the velocity factor. And let's do this exercise because this is a little bit important. So what I want you to do is at this moment is go back and look at the equation for velocity factor. Depending upon what the velocity is, the magnitude of the velocity factor or the equation for the velocity factor is different. So I want you to go to, give me a second here, I'll tell you the equation for the velocity factor. Okay, I want you to go on to page 1039. So please refer page 1039 for velocity factor. And you will realize, depending upon whether it's a ordinary cut gear or carefully cut gear or very accurately cut gear, the velocity factors are different. So as a baseline, and again, this is a design class, so of course there will be some iteration. I will assume the velocity factor to be 3 plus v. This is my assumption. I'm assuming that my velocities, the pitch line velocity Vp, is less than equal to 12.5 meters per second. If this assumption is not correct, for some reason, if you find out that this assumption is not correct, we may have to go back and revise this velocity factor. But at the first baseline, I'm going to assume my velocity factor to be 3 divided by 3 plus v. So what I would do is the value Vp, what I get over here, I will substitute this value in here. And once I do that, recognize my velocity factor, just like the previous problem, will be expressed in terms of module. So this velocity factor will be in terms of module. And in the next step, what we are going to do is we are going to follow the same procedure, and we are going to use the beam strength equation and then determine the module. So it's 7:15. So I'm gonna give you all a break for 15 minutes, and we will continue this discussion at 7:30. So we will stop here for 15 minutes and then we will continue the discussion after 15 minutes. Okay, welcome back. So we will continue the problem. The next step is we have to find out the value of module, and we can assume module to face width ratio. So face width divided by module, and that ratio is anywhere between 9.5 to 12.5. So this ratio is usually between 9.5 to 12.5. So I'm going to assume B by M ratio is equal to 10. Now, what I'm going to do is we have the value of the service factor. So CS is equal to 1. I'm going to find out the value of WT. WT is equal to CS P divided by V. Service factor is 1. The power is given to us 15 kilowatts. So this is 15 10 to the power 3 divided by this value of Vp will be used over here. So you will substitute the value of Vp over here. But important difference here is the starting power is 1.25 times the continuous power. So this is to take into account higher starting torque. So if you look at this entire equation, and I would encourage you to work this equation out, you will realize that the Vp value will be in terms of module. So this entire equation will be in terms of module. So this will be some function of module. So there will be a constant divided by module. And this unit here has to be Newton. So this will be in terms of module. I don't have intermediate answers. So what I will do is I'll give you the steps and then I will give you my final answer. Next step is we have to use the beam strength equation. Beam strength that equation is WT is equal to sigma O multiplied by Y. Since the pinion is weaker, this will be sigma O times YP multiplied by B multiplied by pi multiplied by module. So with this equation, this is the same equation that we used earlier. The only factor that is missing in this equation is the value of CV. So let me write this equation something like this. CV, and this equation is YP. So WT is in terms of module. Sigma naught is given as 200. CV is in terms of module. Please note, VP is in terms of module. Then B, we are going to assume 10 times module. This is nothing but B multiplied by pi multiplied by M multiplied by YP, and YP equation is the same equation since this is given as 14.5 pressure angle. Since the pressure angle is given as 14.5 and it's an involute profile. So they say, so I'm gonna assume 14.5 involute profile. And for that, we will go back and look at the equation for the Lewis form factor, which is y is equal to 0.124 minus 0.684 divided by number of teeth. This equation is given on page 1038. So we can find out the value of y, 0.124 minus 0.684 divided by number of teeth is equal to 25. And we are using 25 because they have specified number of teeth. If the number of teeth are not specified, then you can assume the minimum number of teeth to avoid interference, that is 14, and then solve this equation. So please note, on the left hand side, the equation has module. The right hand side, the equation has module. This is exactly similar to the problem that we worked out earlier, wherein you have a cubic equation and that needs to be solved using trial and error. And again, I would encourage you to actually substitute the values and find the answer. But once you substitute the equation on the left hand side, equation on the right hand side, and then try to find out the answer, you will notice the module is 6 millimeter. So my answer is 6 millimeter. So what you can do is substitute the value for WT. So I'll just make it a little bit simpler. So WT is over here, which is 15 times 10 to the power 3 multiplied by 1.25 divided by VP, which is pi times M multiplied by 75, pi times M multiplied 75 multiplied by 1500 divided by 60. So please note, this is the equation in terms of module on the left hand side, and you have the equation in terms of module on the right hand side. The only unknown in this equation is this guy. And again, VP here, this VP is pi times M times 75 times 1500 divided by 60. So again, it looks complicated, but once you actually work out the values, it's really not. Or you can directly program this entire equation in Excel or Desmos or MATLAB, and you should be able to get the answer. So the answer that I got is 6 millimeter. Now, once the module is known, so module is equal to 6 millimeter, addendum is equal to 1 times module, which is 6 millimeter. Working depth is equal to 2 times module, which is 12 millimeter. And I would encourage you to look at the nomenclature or terminologies that we looked at in the last class. The next part is total depth is equal to 2.25 times m, which is working depth plus clearance, which is 13.5 millimeter. Then you will have to find out the tooth thickness. And please note, tooth thickness is different than the face width. So just to give you sort of clarification, face width is from here to here. This is the face width. And tooth thickness is from here to here. This tooth thickness. Tooth thickness is given as 1.5 times module, which is equal to 9 millimeter. And then you will have clearance, which is equal to 0.25 times m, which is 1.5 millimeter. Now, with this, you have the gear or the pinion designed. So with this information, you should be able to sketch the pinion. You should be able to use SolidWorks and create a model of the pinion. So the next important part is shaft design. So let me consider this shaft design. And as discussed earlier, the configuration of the shaft is not known. So we do not know whether the gear that we have is cantilevered or gear that we have is simply supported. Now, I just want to remind you here that additional complexities are possible. So you can have a simply supported gear, or you can have a cantilever gear. But in some cases, when you go to industry, you may see a gear which is actually supported at multiple locations. So you can see in certain cases, the gears will be located in this case. Please note, in this case, this is a statically indeterminate system. Statically indeterminate system. So if you use a software like ANSYS, or if you use SolidWorks, you can find out the reactions at the supports. And then you can find out the stresses in the shaft. But when we are looking at just machine design, simple machine design, we are going to assume only two cases, simply supported and cantilever, so that we can solve these problems using the equations and the tools that we have available by hand. So now what we are going to do is, we know the value of WT. So WT, as you know, is CSP divided by VP multiplied by 1.25. And once you know the module, once you find out the value of module is equal to 6 millimeter, the values of VP will be known. CS is already known. So you can find out the value of tangential load as 1590 newtons. So this is the value of the tangential load. Now, once you know the tangential load, you should be able to find out the normal load. You should be able to find out the radial load. So as we know, the normal load is WT divided by cosine phi. And once again, so if you look at this gear, and you will notice that the tangential load is something like this. Normal load is something like this. The angle that is made here is the pressure angle, and then you have the radial load. So this is WR, this is WT, and this is WN. And WR is equal to WT tan of P. So WR is equal to 1590 multiplied by tan, and the pressure angle in this problem is 14.5. So tan of 14.5. Now, one thing that we have to understand is the pinion is not weightless. So what it means is pinion has its own self-weight of pinion, and it's non-trivial. How would you find out the self-weight of the pinion? And here is an approximate way of finding the self-weight of the pinion. So assume pinion to be sort of a friction wheel. If you consider the pinion to be friction wheel, then this is the pinion radius, RP. So the area is pi RP square. Volume is equal to pi times RP square multiplied by the face width, because this is the approximate value of B, face width. And then to find out the mass, volume times the density of the material. So if this is steel, so density of the steel is going to give you mass, and weight is equal to mass times the gravitational acceleration. So once you perform these calculations, you should be able to get the weight of the pinion. And my answer is the weight of the pinion is 50 newtons. And this is an approximate way of determining the weight, but it works out quite well in actual practice. So now you have the value of WR. So let's try to find out the easiest configuration that we can consider. So I'm going to assume the pinion is overhang. And again, this is assumption. There is no right or wrong answer here. So I'm going to assume the pinion is overhang. Let me identify or note down the dimensions that we have. This dimension is 60 millimeter. So obvious question is, what should be this distance? And to be honest with you, this distance is depending upon the gearbox design. But in this particular case, I'm going to assume this as same as the face width of the gear. So I'm going to assume this to be 60 millimeter. But again, this is assumption. So unless this value is given to you, you can take this value to be 60 millimeter or 100 millimeter or 120 millimeter, some reasonable value. And once you have that, let's try to find out the total load that is coming on this pinion. So we have WR. Also note, along with WR, we have the self weight of the pinion, which means the total load in the downward direction is WR plus WT, WR plus WT. And please note, this is small WT, this is weight. This is radial load, and this is self weight. Now what's going to happen is this radial load plus self weight is going to give us a component of moment. And let me show you the side view of the gear. In the side view of the gear, then I'm going to have WT. And now I want you to notice this WT is not going through the shaft. This WT is outside. So what this means is essentially on this shaft, I have a torque and I have WT. So what this means, and actually let me write this, show it over here. So if you look at this shaft, on this shaft, I have a force WT like this. What this means is this force, which is at distance RP, is giving me a torque WT times RP, and WT, which is going to the center line. So please note, there are actually two moments acting here. One moment is because of the radial load and the self weight, and the second moment is because of the torsional load. So let's find out the moment. So let's consider the moment in the vertical direction. The moment in the vertical direction is equal to radial load plus weight multiplied by the distance, which is 60 millimeters. Moment in the horizontal plane is WT multiplied by 60 millimeters. So this unit is going to be Newton millimeter. This unit is going to be Newton millimeter. And also I have the torque. This torque is going to be, you can find out the same value of torque that we found out earlier. This is going to be WT multiplied by the radius of the pinion, and the radius of the pinion is 125 divided by 2. This is the radius of the pinion, and you can multiply this by your 1.25 to account for overload during starting. Not cost, overload, which is starting. And this equation is again gonna give you a Newton millimeter. So here is the procedure. M equivalent is equal to square root of mv square plus mh square T equivalent is equal to square root. So this will give you Newton millimeter. So you will substitute this value here, this value here, and next part is MEQ square plus T square. This MEQ goes here, and this T goes here, and that gives you in Newton millimeter. And the last part is, you know, tau is equal to T divided by J multiplied by R. Tau is given to us at 40 Newton per millimeter square. Value of torque is T equivalent. Value of J is pi by 32 d to the power 4. R is d by 2, and the only unknown in this equation is d, and you should be able to get the value of d. So I can tell you that solving this, my answer is 35 millimeters. So I don't have intermediate answers, but I actually substituted all these values directly, and then I found out my diameter is equal to 35 millimeters. But just to point out, it depends upon this assumption of 60 millimeter. It's quite possible that your diameter would be different if you assume that the length of the shaft be greater than 60 millimeter. Okay, any questions here? Now what I want to do is, I just want to take this exercise and talk about how is the housing design. So how to design case or housing. Now, housing dimensions are dependent on how much space we have available. What is the configuration of the gear train? So let's assume that we decide to sketch this gear train, and this is the pinion, and clearly the gear would be 3 times the pinion. So pinion is like this, and you can choose the gear to be again cantilevered. So you have pinion and you have gear. And then what you will do is, you will know the shaft of the pinion. So diameter of the shaft will be known. Then what you do is, you basically do a rough sketching. And now what we want to do is, these bearings are actually housed in the shaft, I mean in the casing. So what I'm going to do is, first I'm going to create a rough layout. This is the rough layout. So this sort of is the rough layout. Now what I'm going to do is, I'm going to add thickness. And clearly I want both of these bearings to be seated at the same location. So I'm going to add this thickness. Then I need to determine the clearances on the either side, so that to make sure that I have space for the lubricating oil. So this is the thickness. And then if I were to look at the side view, the side view would look something like, you have this gear, you have this gear, and then you have this gearbox. And clearly gearbox doesn't have to be circular. I mean, the rectangular. You can potentially, if this is the dimension of your pinion, if this is the dimension of your gear, it's quite okay. And in fact, I have seen majority of the gearboxes to be something like this. Now you will observe that here there will be a shaft. Here there will be a shaft. Around the shaft there is going to be a bearing. There is going to be a bearing. There is going to be seals, and you could have some sort of support so that the gearbox, if it's stationary gearbox mounted like this would be the rough dimension. So this guy is going to go here, this guy is going to go here, and this is how you can sketch the housing. And if you are trying to do this inside SolidWorks, what you do is you first create an assembly of the gear, the pinion and the gear, and then use that to sketch the gearbox around the gears, add some clearance, and then you can actually create, extrude that sketch and create the whole assembly. So it may take some time just to go through this exercise once or twice, but once you are done this exercise a couple of times, you should be fairly comfortable designing the gearbox. Okay, any questions at this point? Now, the next part is design of helical gears. So what I'm going to do is we will start the next topic, and the next topic is helical gears. So what is the difference between the spur gear and the helical gear? So if you look at the spur gear, I'm going to show you a spur gear. Spur gears are cut parallel to the axis. So if you were to look at spur gears, this is the axis of the gear, center line or axis of the gear. Spur gear is cut parallel to the axis. But if you see a helical gear, the helical gear are cut, the teeth are cut at an angle. So if you look at the helical gear, and this angle is called as the helix angle. So if you look at the center line, this is the helical gear. Now, why do we need to cut the gears at an angle? Why not maybe just have the spur gears? the advantage of helical gear is if you look at the face width for the same dimension, if you look at the face width, helical gear face width is larger than the spur gear. So face larger, face width. In other words, for same size, they are stronger. Clearly, the area is more, so the load bearing capacity is more. They are stronger, the engagement is smoother. Then the other thing is they are actually sort of quieter, that leads to high efficiency. So they have slightly higher efficiency than spur gear. And when you are trying to cut a helical gear, the idea is instead of aligning the cutter parallel to the shaft axis, you have that at a helix angle. Now, what is the disadvantage of helical gear? Now, please understand, there are two types of helical gear. So one is a single-sided helix. So you have a single-sided helix. So you have a single-sided helix. Or you could have a double-sided helix. So what happens in the double-sided helix is you have helix on both the sides, and that is sometimes called as herringbone gear. So you could have helix on both sides. So you have, this is the helical gear, this is double helical, or herringbone. Now what happens in the helical gear, I just want to show you that the force that is transmitted is in this direction. What that means is this force that is transmitted around the normal direction has a component along the radial direction and another component during along the axial direction. So during power transmission, you have the normal force that is aligned at an angle, helix angle. So what happens is whenever you have a helical gear, you are gonna get a side thrust. But if you look at the double herringbone gear, you are gonna have a side thrust from the left hand side, and you are gonna have a side thrust from the right hand side. Since there are two helix, there is no effective side load in the double helical or herringbone gear. But if you use the pure helical gear, you are gonna have the side load. And sometimes this side load is desired. A classic application is, say you have a clutch. And we briefly talked about clutch and clutch plates. So you have a clutch. And on one side of the clutch, what you have is you have a helical gear. So what's going to happen is because of the helical gear, there will be a pressure on the clutch plate. So you don't have to actively apply the pressure on the clutch plate using spring. You can have springs, but they don't have to be that strong, because as soon as the power transmission starts, the helical gear is going to add its own thrust onto the clutch plate. So if you have, this is the clutch, and this is the helical gear. So the helical gear is going to give axial thrust on the clutch plate that may be desired in certain conditions. Now, some important definitions in helical gear. It first is helix angle. Helix angle is the angle made by the face width to the axis of rotation. So this angle is usually called as alpha. Helix angle is alpha. Now there are two types of pitches. So this is a normal pitch. So you have something called as normal pitch, which is Pn, and this is normal to the face width. And then you have something called as the axial pitch. Which is PC. And the relationship between Pn and PC is equal to PC cosine of alpha. So PC multiplied by cosine of alpha, where alpha is the helix angle, you get the normal pitch. Now, what does that mean in terms of the gear design? So when we design a helical gear, here is a general strategy. What we are going to do is we will convert the helical gear into an equivalent spur gear. So we are trying to design a helical gear, but helical gear is sort of the spur gear but at axis. So I'm gonna follow the same design procedure for the spur gear, but I'm gonna convert this helical gear into an equivalent spur gear. And again, how is it done? So if you have a helical gear of number of teeth, so let's consider a helical gear. So helical gear has number of teeth Tg. Tg are number of teeth. So equivalent number of teeth on spur gear is equal to Tg, and this is an important relationship, cosine cube alpha, where alpha is the helix angle. And helix angle for the gear can be different. So pressure angle, so I'll write this down. Pressure angle for helical gear is in the range of 15 degrees to 25 degrees. And the helix angle for helical gears is 20 to 45 degrees. The addendum is equal to 0.8 times module. And please note, for spur gear is usually 1 times the module. Dedendum is usually 1 times module. Total depth is equal to 1.8 times module. Minimum clearance is equal to 0.2 millimeters and 0.2 times module. And thickness is usually 1.5 times module. So these are the standard dimensions for the helical gear. So how would we design the helical gear? So here is the process. Consider a helical gear. Find out the number of teeth for the helical gear. The next step is find the equivalent number of teeth for the helical gear, which is Tg divided by cosine cube alpha, and follow the exact same procedure. So which means find tangential load, find whether pinion is weaker or gear is weaker, then find module using beam strength equation, then find out the value of dynamic load, then find out the wear load, and then find out the static load, and make sure that the dynamic load is less than wear load. Make sure dynamic load is less than static load. Now, a word of caution or something to take into account. I have uploaded additional examples and videos for spur gear on Canvas. So please watch those. So I have tried to work out the problems that were not previously discussed. So please, before you solve the homework or the quiz problem, I would strongly encourage that you take a look at the PowerPoint slides and notes that where I worked out additional problems, and also the videos where the additional problems have been solved. Okay, so please, when we do this, from here onwards, we will use the tables in spur gear chapter. So spur gear chapter, which is chapter 28. So when we are going to solve the helical gear, as soon as we convert the helical gear into an equivalent spur gear, all the equations, all the formula, all the strength values that are given in the spur gear will be applicable. So what I'm going to do is, rather than solving or giving you the design steps, let me jump into the problem. And I will try to solve this problem where we find the dynamic load, we find the wear load, we find the static load, and so on. So this will give you some idea if you are given a spur gear problem with all those properties, how would you solve these? Okay, before I work out a helical gear problem, any questions? If you have any questions, just raise your hand or you can type the question in the chat window. Okay, now let me take a problem. Helical gear power transmission is equal to 15 kilowatts. It's 20 degrees stub. The helix angle is equal to 45 degrees. The pinion speed and pinion is 10,000 RPM. This is a high speed transmission. So pinion speed is 10,000 RPM and the diameter or PCD of pinion is equal to 80 millimeters. PCD of gear is equal to 320 millimeters. And the material, it's a cast steel with strength, which is sigma O, is 100 Newton per millimeter square. Now determine the module. So design the gears. And sigma ES is 618 Newton per millimeter square. So in this problem, sigma ES value is given to us. Now, since pinion and gear are of same material, pinion is weaker. So what we are going to do is we are going to design the pinion. So step one, we are going to find out the torque that is transmitted by the pinion. P is equal to 2 pi nt divided by 60, which is 15 10 to the power 3 is equal to 2 pi 10,000 times t divided by 60. So you'll get the value of t, and the answer I got is 15 Newton meter. Now we want to find out that the tangential load on the pinion, which is Wt, is equal to torque divided by the diameter of the pinion divided by 2. So torque is equal to 15. Diameter of the pinion is given to us as 80 millimeters. So 80 divided by 2, need to convert torque in millimeters. So that gives me the answer 360 newtons. Now, in this particular problem, the diameter is given to us. Number of teeth, uh, they are actually in this particular problem are not known. But what I'm going to do is I'm going to assume module is equal to m. Thus, number of teeth on pinion is equal to diameter divided by module. So 80 divided by m is equal to number of teeth. Now here at this point, this is the number of teeth on the helical gear. This number of teeth needs to be converted into an equivalent number of teeth for the spur gear. It will be 80 divided by m multiplied by cos 45 cube, which happens to be 227 divided by m. So the equivalent number of teeth are going to be 227 divided by m. Now please note, as soon as you find out TE, you will continue with the spur gear design procedure. So as soon as the equivalent number of teeth are found, that means we have converted that helical gear into an equivalent spur gear, and we are going to use all the relations, all the equations, all the tables that we use for spur gear design. So obviously the next step is determination of form factor YP, and I'm going to say prime just to indicate this is for the helical gear. So this is for the helical gear, and the equation for the helical gear that comes from the same equations, same set of equations that we have for the spur gears, and the equation is for 20-degree stub is 0.175 minus 0.841 divided by equivalent number of teeth, which is 0.175 minus 0.841 divided by 227 divided by m. Once again, you will notice that this equation will, all these equations will be in terms of m, and finally we will compare the equation for m using the beam strength equation, and the left hand side would have m, right hand side would have m, and we'll solve that equation using trial and error. So this equation is nothing but 0.175 minus 0.003 m. Now velocity of the pitch point is pi times diameter of pinion, speed of pinion divided by 60. So which is pi times 0.08 multiplied by 10,000 divided by 60, which gives you 42 meters per second. Now, please understand this is quite high velocity. So we have to use the velocity factor for velocities greater than 20 meters per second, as Vp is greater than 20 meters per second. The velocity factor is 0.75 divided by 0.75 plus square root of Vp. 0.75 plus square root of 42, and that answer is 0.104. Now the phase width, so it is something interesting to notice that since the helical gear, if you look at the way the helical gear are constructed in comparison with the spur gears are like this. The helical gears are like this. So phase width for the helical gear is going to be greater than the phase width for the spur gear. So this is spur gear, this is helical gear. So phase width for the helical gear is greater than the phase width for the spur gear. So typically the equation is 12.5 module to 20 module. And if you recollect, for spur gear, our range was between 9.5 to 12.5. But for helical gear, since the phase width is at an angle, usually that value is taken as 12.5 m to 20 m. So let's assume B is equal to 12.5 times m. Now, what we know here is we know the value of Wt, we know the value of sigma O, we know the velocity factor multiplied by B multiplied by pi multiplied by m multiplied by yp prime. So Wt is 360 from the last equation. W naught is 100. Velocity factor is 0.104. Phase width is 12.5 times m pi m, and yp is 0.175 minus 0.003 m. So the only unknown in this equation is m. And the answer for m is 2.5 millimeter. So when you solve this equation, the answer, at least I got, is 2.5 millimeter. And the phase width B is equal to 12.5 times 2.5, and the answer is 32 millimeter. So phase width is never in fractions. So phase width is always a whole number, and whatever value you get, you round it on the higher side. So next part is checking gear for wear. So next step is checking gear for wear. So let's find out the reduction ratio or velocity ratio. It is also called as the reduction ratio, which is the diameter of the gear divided by the diameter of the pinion. Diameter of the gear is 320, diameter of the pinion is 80. So the reduction ratio is 4. Now, next step is we need to get the value of ratio factor. This ratio factor for the external gearing, since you have this pinion and the gear that are meshing externally, not internally, these are meshing externally, it is 2 times VR divided by VR plus 1, which is 2 times 4 divided by 4 plus 1 is equal to 1.6. Now, something that you have to be clear about is we want to find out the pressure angle in the normal plane. So phi n, and we'll talk about this in little bit detail, is the pressure angle in normal plane. Because please understand, when you're looking at the helical gear, you have helix angle, and that helix angle is at an angle alpha with respect to the center line of the shaft. So when we are trying to find out the value of phi for the helical gear, this is an important relationship that you should keep in mind. Tan phi of n is equal to tan phi times cosine of alpha. So this is an important relationship. Now I want you to compare this relationship for a spur gear equation. For spur gear, alpha is equal to 0. What that means is cosine alpha is going to be 1, which means the pressure angle in the normal plane is equal to the pressure angle that you have. That's why we don't use this relationship in the case of spur gear, but in the case of helical gear, since that you have angle at an helix, you have to find out the value of pressure angle in a normal plane, which is tan 20 times tan of 45 is equal to tan phi of n, and from there I get the value of phi of n is 14.4 degrees. And I will discuss this in detail, to be discussed in detail in next class, because this needs a little bit more geometrical intuition. So I will draw the 3-dimensional sketch, and then I will show you what exactly the meaning of phi n. But at this point, I want you to understand phi n is the pressure angle in the normal direction, and that pressure angle in the normal direction is not equal to pressure angle because there is a helical angle coming in the picture. Now, the Young's modulus for steel is 200 kilonewton per millimeter square. So load stress factor K, which is the load stress factor, is equal to sigma ES square sine phi n divided by 1.4, 1 divided by the Young's modulus of pendulum, Young's modulus of pinion, and Young's modulus of gear. So E is equal to EP is equal to EG. And since sigma ES is given to us, sine. Here this is Cn, which is 14.4. Divided by 1, 200, 10 to the power 3 plus 1 divided by 200, 10 to the power 3. And that gives me 0.678 Newton per millimeter square. And the wear load is given as dP B Q K divided by cosine square alpha, which is 80, 32. The value of Q is 1.6 that we already found out from here, which is ratio factor. Q is ratio factor, is 1.6 multiplied by K divided by cosine square 45. So this answer is 5 kilonewton. And please note the wear load, the maximum load is less than, or the maximum load or tangential load, maximum load in tangential direction is less than max wear load. So I think it was 380. So let me see what was the tangential load. It's 360. 360 is less than 5,000, which means the design is safe. So again, in this, there are various options available to us when we design, but we'll start with a very simple approach, and then we'll try to look at more complicated designs. So with this, I'm going to stop here. If you have any questions, feel free to ask me now, or send me an email, or type questions in the chat window, or raise your hand and I will unmute you. So that's it for today, and I will see you all next week.